covered last Wednesday. Last Wednesday, we talked about Faraday's law, so now we have time-varying magnetic field. Faraday observed, due to his experiments, if you have a time-varying magnetic field, so now you see this time variation, you can create a non-conserved electric field. He wrote down these equations, and then we talked about the importance of this negative sign. Negative sign means a 180-degree phase difference. And now you have a time variation, exponential j omega t. Whenever you have a time derivative, you multiply by j omega. So together, you have a 90 degrees phase delay, right? This is written in the differential form. You can also write it in the integral form. Okay? So this means, together, the time variation can be decomposed into two components. The time variation can be showing in the magnetic field, or you can also have the circuit area, which is time varying. Okay? Last Wednesday, we talked about the first case. We only have a time-varying magnetic field, but the circuit remains stationary. Okay? So the circuit is not moving. It's only the field line. The number of the field line is changing against time. So for this particular case, the E that is induced is called the transformer EMF, electromotive force. BT, T stands for transformer. So all we have to calculate is the magnetic flux as a function of time. And we find out how it changes against time. And still remember, you have to include this negative sign, right? So basically, transformer EMF, your circuit is fixed. It's not changing. It's not moving. It's only the field that is changing, right? But you have to think, why is that particular case called the transformer EMF? So now we deal with transformer. To my best knowledge, everybody here passed the course called electric circuit, right? Assume. That's my naive assumption. But of course you hate that course and you don't remember anything. But you must have heard the word transformer. So when you think about transformer, when you hear transformer, what kind of picture comes into your mind? For me, I grew up watching this, so whenever I hear transformer, I don't really have the electric circuitry that we're using, but I think of this bumblebee, right? This is everybody's good friend. A transformer. It's just a joke. For the course called electric circuit, everybody learned, you were forced to learn the transformer. And probably starting from high school, I still remember my high school year, having to remember or memorize all the relationships for a transformer. So what is a transformer? A transformer is having a magnetic core, right? A magnetic material. And then you have two coils, wires, winded on this core. So usually you have the winding one having number of N1 coils, and you drive this coil. But somehow, you really connect your device on the second coil. So the second coil can have a different winding number, N2, right? So basically, that's a transformer. Everybody here knows what a transformer does, but let us come back to why this case the induced EMF is called the transformer EMF. Because in the transformer, not bumblebee, okay, the real device transformer, what is changing as a function of time? You apply either voltage as a function of time, or effectively, you're applying the current as a function of time, right? So whenever you change the voltage or current driving the first circuit, the first winding, you are changing your number of magnetic field lines, right? But then you ask yourself, is the entire device moving? No, the entire device, you want to make it fixed in space, right? So this description perfectly fits this one. Your surface area or your device is fixed in space. What is changing is your number of magnetic field line, right? And therefore, this particular case adopted the name transformer EMF. It's identical to a transformer, how a transformer works. Okay? Now, having this picture, and we understand why this particular type of EMF is called transformer EMF, because you want this device to remain stationary. You only change its phi, the magnetic flux, right? Okay, knowing this device, how do we write down the first equation? The first equation is always the most difficult. But in the end, our target is to find out the relation between V1, that is the voltage you apply. You want to know what is V2, right? If you send in, if you drop in $10 and you can get $100 here, that's the best, right? You go to the post office, you mail 10 max to your relative in the United States, and in the end, they receive 100 masks. That's great, right? And we also want to know I1 and I2, how they are related. But if you want to know this electric properties, voltage and currents are actually electric properties. How can you link voltage 1 to voltage 2 or current 1 to current 2? What is the thing that's connecting these two independent coils? Coil number 1 might be in Taiwan, coil number 2 might be in the United States, right? If you have a big magnet. And these two are actually independent. So how are they interlinked? They're interlinked through magnetic flux. So basically, you're dealing with a magnetic circuit, which we talked about maybe 2 weeks prior to this class. Okay? So if you still remember, this is the so-called Kirchhoff's voltage law in magnetic circuitry, right? In magnetic circuitry, all you care about is the number of current. The number of current is used to produce the magnetic field lines. These two coils are interconnected or linked through the magnetic field lines, right? If you have one more line, the line passes through the second coil feels its presence and reacts, right? Do you still remember what this is? It's called the reluctance, okay? 磁阻 reluctance, and this is phi. the magnetic flux. Together, this equation is almost like saying VI equals sigma R times I. Right? In magnetic circuit, the magnetic flux is having the equal functionality as current in an electric circuit. Right? So this is the equation we are going to borrow, okay, for this particular device. We have a transformer. So how to write it down? We have the summation signs. Right? So in this particular case, how many current sources do we have? We have current 1, winding number 1, current 2, winding number 2. So summation sign usually means you add, right? The number of coils, the number of currents, you basically add them up. But in this case, you have to be extremely careful. Why? If you still remember, current comes in different directions, right? Once the current direction is determined, the resulting magnetic field line direction is also determined. So for this case, for coil number 1, it is winded in a way your wire goes on top of the coil, right? So the core is having magnetic field lines. So in this case, when your current I1 is coming in, you generate an upward magnetic field line. Okay? Let's take a look at coil number 2. Coil number 2 is also having the wires coming on top of the core, right? So if you have current number 2 also conducted, it also generates field lines pointing upwards. So what does that mean? It means if I1 and I2 are in phase, they're having the same phase. If this is cosine omega t, this is also cosine omega t, they have no phase difference. And they have no difference in the direction, right? They have both positive. When they are in phase, they generate field lines both upwards. What does that mean? That means the field lines actually cancel out, right? So these two current sources are viewed to counteract each other in the current configuration due to this winding directions. So the best way to write it, summation sign, is saying you add them together, but in this case, the magnetic flux generated by coil number 2 is used to cancel the magnetic flux created by the first coil. So you need to adopt this negative sign. Okay? So N1I1 minus N2I2 is your resulting magnetic flux multiplied by the reluctance. Here you only have one device, right? The only device is this magnetic core. Alright, such a simple equation. What is the assumption behind it? You cannot find a simpler equation than this. Right? But there is a basic and a very strong assumption behind it. What is the assumption? How can you say there is only one reluctance? Or when you view this equation, you should be very clear what is assumed. this is assuming all the field lines generated by these two coils are completely guided in the core. Right? You have no leakage. If you have leakage, for example, one line is leaking from here, comes back, right? Then you have leakage. If you have leakage, you have to add the leakage flux. Okay? So already, with this equation, we have assumed we have very good magnetic core so that basically all the field lines generated by the coils are well guided or spatially confined within the magnetic core. So therefore, if you generate one more line, that line is perfectly transmitted to the second coil. They communicate in the perfect sense. Okay? Now, under that assumption, we can say that, oh, this transformer is basically ideal. What does ideal mean? Ideal means you have no leakage flux, right? All the magnetic field lines created by the coil are completely guided by the core, and therefore, basically, you are using a magnetic material with extremely high mu. Right? That is your basic assumption. If your mu is not very high, you expect to have leakage, and your equation has to be modified. Okay? So since we wrote this equation, we made our assumption. This assumption is now explicitly mentioned. Mu is reaching infinity. We have a very good core material. If we have a very good core material, then the reluctance, the length, the round trip length, divided by the surface area and divided by mu is approaching to 0. Right? So for a perfect or an ideal transformer relies on no leakage flux because we're using a very, very good magnetic core. So in that case, the reluctance is 0. If the reluctance is 0, here reluctance multiplied by phi is approaching to 0, then N1I1 minus N2I2 is equal to 0, or almost equal to 0. And that is the starting point in your past learning experience. In high school, you were forced to accept an ideal transformer has this relationship. And even in your first year of college, fundamental physics, all the professors taught you again, ideal transformer, N1I1 equals N2I2. But you never asked why. And now that you know, if you have an imperfect transformer, when mu is not very large, you have to go back to this equation. You have to solve this equation. But once you have the starting equation, with your mathematical skills, you can solve everything. Right? So this is the process of learning the real picture. Initially, you were given the result, but now you know the reason behind this ideal transformer. Okay? So since N1 times I1 is equal to N2 times I2, this is what you remembered. The currents on the two coils are inversely proportional to the winding number. Right? I1 to I2 ratio is N2 to N1, so it's inversely proportional to the winding number. What about voltage? Well, voltage for each coil is d phi dt, right? This is what Faraday taught us. And you multiply by the winding number. under the assumption we have perfect transformer, phi has to be equal for both coils, right? All the field lines are confined by the coil, so coil number 1 and coil number 2 share the same number of magnetic field lines, and therefore the magnetic flux will be the same. In this case, your voltage is proportional to the winding number, and therefore this is what you remembered. The voltage ratio is proportional to the winding number, right? But the current is inversely proportional to the winding number. You don't really have to memorize anything once you understand how a magnetic circuitry works, right? This is a Kirchhoff's law. This is Kirchhoff's law for the electric circuit, and this is the equivalent form for a magnetic circuit. Okay, so once you know this, once you know the physical meaning and the operational principle, you don't really have to memorize anything. All right, so power equals V times I. So basically, the power remains a constant on both coils, right? We are viewing the transformer as a magical black box. We don't really know what's happening inside, but we know our load. Our load is your device to be used, to be connected. Okay? So this is saying that you only know your driving voltage, you know your driving current, but then somehow that is transformed to the other side, to the device. But the device can have different operational V, operational I, right? So basically what we know is the impedance or the resistance, effective resistance is V divided by I. V divided by I. Okay. For the load, your load resistance is V2 divided by I2. But that is going to be transformed to your driving side. To your driving side, V1 divided by I1 is not equal to your load. Okay? Because you have this weird ratios between the terms. So this is also what you memorized in the past. The effective resistance or the load seen by the first coil, your driving side, is your real load multiplied by the square of the winding number ratio. Okay. So now you have the complete information. You should ask yourself, what is the basic functionality of a transformer? A transformer can change the load impedance, right? By changing the number of the winding number. You can change your effective impedance. So this is pretty much another way to perform maybe impedance matching. Right? Another sense is, well, you can potentially use a very low driving current. The current that you send in can be very small, but the current coming out and into your load can be made very high. Okay? This is like almost like earning free lunch. But eventually the power remains constant. So if your I2 is made extremely high, your V2 has to be low. Okay? So this is a perfect device Do you listen to music? Well, if you listen to music, here we have a speaker, right? Here we have a speaker. Usually, when I speak, my voice, the sound, is driving my microphone. So I have a capacitor inside the microphone, and when I speak, it is giving some pressure. The air is vibrating, giving the pressure to this microphone, so I have a membrane. This membrane is changing, deforming, therefore changing some voltage. Okay? But usually the speakers are driven by currents. Okay? So you somehow need to convert from voltage signal into current signal. And if you want to make your speaker sounding very loud, you have to send in large current. So the transformer is the ideal device, right? You can pretty much convert your power. Your power remains a constant between the two wires, but maybe the first coil is having a large proportion of energy stored in voltage. But now after the transformer, you can transform to the majority part is experienced or behave as a high current and low voltage. So this is the engineering capability provided by a transformer. Okay? So please do remember this life case, the sound. You are enjoying this benefit every day. If you open up the case for an amplifier, you see a large coil. So you always have transformers. Okay? So transformers give you the freedom to interchange voltage to high or low current to low or high current, or vice versa voltage. Okay?